Welcome to the second lecture of this week. In the last class, we discussed about the first order shear deformation theory, and we have seen we started with the kinematics of that, and then based on that we derived the relation between the stress resultants, that means the forces, moments and the displacement components. Now, apart from u0, v0 and w, we have psi x and psi y also as the variables which is needed to define the deformation of the laminate. So, there are 5 variables now. So, today we will look at the governing differential equations and then we will go for the solution. So, when we deal with the classical laminate theory, what we did was that we derived 5 equations. First, the in plane equations along x and y, and then a equation out of plane equation, I mean the balancing the forces along z direction, and then 2 moment equations. And then we substituted the 2 moment equations, we put the 2 moment equations in the out of plane equation, and then we got on one equation. That way we eliminated 2 equations and we dealt with 3 equations. Now, here we have 5 variables, so we will deal with all the 5 equations. So, the in plane equations are del n x by del x plus del n s by del y minus I 0 u 0 double dot plus I 2 psi x double dot equal to 0. So, here we can see previously it was minus I 2 into del w double dot by del x, because psi x was minus of del w by del x. The next equation along y direction is del n s by del s plus del n y by del y minus I 0 into v 0 double dot plus I 2 into psi y double dot. Same thing here, previously in the classical laminate theory it was minus I 2 into del 2 w double dot by del x del y. Here it is plus I 2 psi y double dot. Then the equation that we get by equilibrating the forces along x direction. So, for that we have del v x by del x plus del v y by del y plus q x minus I 0 w double dot equal to 0, same equation. And then the moment equations are del m x by del x plus del m s by del y minus v x minus I 1 u 0 double dot plus I 2 psi x double dot equal to 0, and then we have del m s by del x plus del m y by del y minus v y minus I 1 v 0 double dot plus I 2 psi y double dot equal to 0. So, these are the first these are the 5 governing differential equations we have to deal with. Now, when we solve a static problem, we ignore the inertia terms, and when we solve a free vibration problem, we have to ignore the force. So, these are the 2 type of problems we will deal with here. So, we will consider first a simply supported cross ply laminate. So, our laminate again the same geometry we have been considering so far, x y, the dimension is a, here the dimension is b, and all the edges are simply supported. Now, our first job is to put the differential equations, put the relations between the force and moment components with the displacement components in the differential equation, and that is how we can be able to write the, that is how we will be able to write the differential equations in terms of the displacement components. So, if I write the first equation nx del nx by okay. Now, because this is simply supported cross ply and also it is symmetric. Now, because it is symmetric, so we have B matrix 0. So, we will not deal with these two equations, we will deal with only these three equations. And also here because it is simply supported cross ply, so it can be shown that Vx, Vy are just Axx z 0 0, Ayy z 0 0, and then we have del w by del x plus psi x and del w by del y plus psi y. In cross ply laminate, all the plies are in the principal material direction. So, there is no coupling between the shear terms. So, that is why the coupling term Ax y z is absent here, and this simplifies the differential equation. So, the first equation, the equation that we get from this del Vx by del x plus del Vy by del y plus q minus I0 w double dot equal to 0, that equation becomes del by del x multiplied by del by del x of Ax x z into del w by del x plus psi x plus del by del y of Ayy z into del w by del y plus psi y plus q minus I0 w double dot equal to 0. Then the equation from the moment that we get is del mx by del x plus del ms by del y minus Vx minus I1 u0 double dot plus I2 psi x double dot, that equation becomes del by del x of dxx into del psi x by del x plus dxy into del psi y by del y, and then we have del by del y of dss into del psi x by del y plus we have dss of del psi y by del y plus we have del by that is what we have, and then we have the inner shear terms, and those terms are then we have the minus Vx term, and for that we have Axx z into del w by del x plus psi x, and then we have minus of I2 into psi x double dot. And then from the third equation we have del ms by del x plus del my by del y minus Vy minus I1 V0 double dot plus I2 psi y double dot equal to 0, but again like here also we have neglected the inertia term. So, u0 I is dropped. Similarly, we will drop this term also, and after that we will get del by del x of dSS into del psi x by del y plus dSS into del psi y by del x plus del by del y of dxy into del psi x by del x plus dyy into del psi y by del y, and minus we have ayz into psi y plus del w by del y minus I2 into psi y double dot equal to 0, and here also V0 double dot dropped. So, there is no coupling between the in plane and out of plane terms. Now, this is a second order differential equation. Finally, this term becomes dSS into del 2 psi x by del x del y. This becomes dSS into del 2 psi y by del x 2, and so on. And similarly here also. So, all these terms which which comes from the material properties is dxx, dss, axx, and all these constants from the ABD matrices, and this matrix they are all I mean independent of x y. So, finally, they come out, and this, and we can rewrite the equation. Now, we have to look at the boundary conditions. So, since it is symmetric, it is simply supported. So, the boundary conditions are at x equal to 0 and a and y equal to 0 and b, we have w equal to 0, and at x equal to 0 and a, we have mx equal to 0, and mx is we know nothing but minus dxx. So, it is not minus now, it is dxx into del psi x by del x plus dxy into del psi y by del y, and y is equal to 0, and at y equal to 0 and b, we have my equal to dxy into del psi x by del x plus dyy into del psi y by del y, both are 0. So, we will do Navier's solution here. And for that, we assume that w as a function of x y is equal to summation 1 is equal to n equal to 1 to n, m equal to 1 to m. We have Wmn into sine m pi x by a sine n pi y by b, and then psi x we assume it to be, okay, so let us write it just up to infinity, but anyway when we do the solution we truncate it up to a term m and n, and for that we have, let us bring a new constant capital X m n that is associated with psi x, and psi x becomes a function of this type cosine m pi x by a into sine n pi y by b, and psi xy as psi y, let us assume it to be a cosine sine function. Sine m pi x by a and cosine n pi y by b. So, we can see that if I substitute these assumptions in the differential in the boundary conditions, they satisfy both essential and natural boundary conditions. Now, if the problem is time dependent problem, in case of time dependent problem or the vibration problem, in case of, so the all the developments we will incorporate both the inertia and the load, and then we will see how we can do we can drop out the load and do a free vibration analysis, and then drop out the inertia term and do a static analysis. So, we will do a generic development here. So, in case of vibration problems, W is becomes a function of x, y, z, x, y and t not z, and then it looks like this: n is equal to 1 to infinity, m is equal to 1 to infinity, and then we have Wmn sine m pi x by a sine n pi y by b, and then it is a function of time, and for that we write this as, we separate out a term e to the power I omega t. Now, please understand this omega is can be different for each combination of m and n. So, we can write omega m n also. Now, psi x y t is also like this: n is equal to 1 to infinity, m is equal to 1 to infinity. So, we have capital X m n, we have capital X m n, and then cosine m pi x by a sine n pi y by b e to the power I omega t, and then we have psi y x y t, and then we write this as n is equal to 1 to infinity, m is equal to 1 to infinity, y m n sine m pi x by a cosine m pi y by b e to the power I omega t. Now, if I put these approximations in the differential equation, then what we get is, so before that, yeah. So, these are the differential equations written in terms of the displacement components. So, putting these approximations, in the governing differential equations, we get this in this form. So, from the first equation we get, so let us number the equations, that will be easier. So, here let us call this as equation 1, let us call this as equation 2, and let us call this as equation 3. So, equation 1 becomes n is equal to 1 to infinity, m is equal to 1 to infinity, and then we have minus m pi a into capital X m n. So, this term comes from del psi x by del x, and from then we get m square Yes. So, from del psi x by del x we get this term, and then we have second order derivative of w. So, we will get m square n square by a square w m n, and this is multiplied by a x x of z, and then for the then we get minus n pi by b y m n plus n square pi square by b square w m n into a y y z, and then we have plus q m n and plus I 0 omega square w m n. So, we have a term minus I omega I w double dot. So, w double dot is nothing but minus of omega square w m n, and then finally, it is multiplied with sin m pi x by a sin n pi y by b equal to 0. Now, we have seen that the load q as a function of x y is expressed as a double Fourier series n equal to 1 to infinity, m equal to 1 to infinity, q m n multiplied by sin m pi x by a sin n pi y by b. So, that also has been put in the differential in the first differential equation. So, that is why we get q m n here. We discussed this when we discussed the Navier solution first for static problem. Now, from the second equation we get from the second differential equation we get n is equal to 1 to infinity, m is equal to 1 to infinity. We have inside a third bracket minus m square pi square by a square into x m n dxx minus m n pi square by a b dxy into y m n, and then we have minus n square pi square by b square dss into y m n minus m n pi square by a b dss into, sorry, this is x m n and then y m n. X m n in here y m n minus a x x z m pi by a w m n plus x m n, and then we have plus I 2 omega square into x m n, everything multiplied by cosine m pi x by a sin n pi y by b equal to 0. Then we have the third equation, and from this we get n equal to 1 to infinity, m equal to 1 to infinity, and then we have dss multiplied by minus m n pi square by a b into x m n minus m square pi square by a square into y m n, and then we have minus of m n pi square by a b into dxy into x m n minus n square pi square by b square into dyy into y m n. So, this bracket is not required here. into ymn, and then we have minus ayyz into n pi by b multiplied by wmn plus ymn, plus we have omega square y2 ymn, and this entire thing is equal to 0. So, this is quite straightforward. We have these assumptions. So, when we differentiate them, some terms like m pi a by a or n pi y by b comes out, and if we just be consistent with our formulation, finally we can get these three algebraic equations, linear simultaneous algebraic equations. Now, when it is a static problem, we do not have these inertia terms. So, the qmn is known to us and our unknowns are wmn, xmn, ymn. When it is a free vibration problem, qmn is not there, our unknown is omega square, which you have to solve, and once we know the omega square, we get the xmn, wmn and ymn, and those are the eigenvalues. So, let us consider the free vibration problem first. So, free vibration problem means the static load, there is no load is not incorporated. So, qmn is not considered in these algebraic equations. So, if we arrange the equations in a matrix form, it looks like this. So, it takes a shape of this k multiplied by x mn, y mn, w mn is equal to m multiplied by x mn, y mn, w mn, and this is for each combination of m and n. So, here the K matrix is this, it is a 3 by 3 matrix. So, the matrix is m pi a x x z by a. Here we have n pi a y y z by b, and here we have m square pi square by a square a x x z plus n square pi square by b square a y y z. This is the first row. The second row is m square pi square by a square into dxx plus we have n square pi square by b square multiplied by dss, and then we have plus a x x z. Then the second diagonal term, that is m n pi square by a b, and that is multiplied with dxy plus dss, and then we have a x x z m pi by a, and then the third row, it starts with m pi a square mn pi square by a b, and that is multiplied with dxy plus dss, and then we have m square pi square by a square into dss plus n square pi square by b square multiplied by dyy, and then we have plus ayy z, and then the last term is ayy z n pi by b. So, this is our K matrix, and M matrix is, it is a diagonal matrix. So, here we have I 0 0 0 0, I 2 0 0 0, I 2, and also omega square term should be there. Now, this is an eigenvalue problem, and if I solve the eigenvalue problem, I get omega square as the eigenvalue, and we get that for each m and n, and here I can get 3 omegas. So, these are the 3 natural frequencies that we get for each combination of m and n, and for each omega then we can get an eigenvector, and from there we can define the mode shape. So, this is how we solve the free vibration problem. Now, for static problem, we do not have the inner shear terms, and here we have the QMN term coming into picture. So, in that case we have QMN, YMN, XMN, YMN and WMN, and then in the right hand side we have QMN 0 QMN. Zero QMN. So, if I look at the equations, so from so it is in the first equation. So, yeah, so this equation is the equation corresponding to W. So, QMN should be there, not in the last equation. So, we have 0 here and QMN here. So, for free vibration we have dropped QMN, and for static problem we dropped the inner shear terms, that means the terms which has omega square associated, that means terms with omega square. So, here we did a combined formulation, and previously we did the static problem and natural vibration problem, free vibration problem separately. Here we did it, we showed the combined formulation, and then where we look at the specific cases. So, this brings us to the end of this lecture. Thank you.